This online tutorial is about enthalpimetric Lewis acidities and basicities. Enthalpimetric Lewis acidities and basicities measure enthalpies to quantitatively express Lewis acidities or basicities. While enthalpies don't include entropic effects, there exist relatively easy and accurate ways to measure enthalpies, and enthalpimetric Lewis acidities and basicities have proved themselves to be useful in prediction, justification, and in general analysis of acid-base behavior of Lewis acids and bases. Therefore, enthalpimetric Lewis acids and basicities are among common ways to quantitatively express Lewis acidities or basicities, and it is very important to be familiar with them in context of Lewis acid-base strength. Here, I'm gonna talk about common terms and quantities for enthalpimetric Lewis acidities or basicities. Proton affinity is among well-known enthalpimetric basicities. Proton affinity is the negative of the enthalpy change for the reaction of addition of a proton and H plus cation, a hydrogen cation, in the gas phase. The general form of the reaction can be written as follows: base in gas phase plus H plus a proton yields BH plus. Proton affinity is often abbreviated as PA. Proton affinity is the negative of enthalpy change for this reaction. In the gas phase, we don't have any solvation effects, so proton affinity can be considered as an inherent measure of basicity. While it is common to consider proton affinity as a quantitative measure of Bronsted basicity, since all Bronsted bases can also be considered as Lewis bases, we can also consider proton affinity as a quantitative measure of Lewis basicity. Although we should pay attention to the fact that among different Lewis acids, proton in gas phase, H plus in gas phase, is very different and specific. It doesn't have any inner electrons, a property which is not shared by other Lewis acids. Based on acid-base theories, especially Usanovich acid-base theory, acids are donors of positive species or acceptors of negative species. On the other hand, bases are donors of negative species and or acceptors of positive species. In this regard, among chemical species, proton and electron are specific and fundamental in the context of acids and bases, analogous to proton affinity as a quantitative measure of basicity. Electron affinity might seem as a good candidate as a quantitative measure of acidity. Electron affinity is the energy required to detach an electron from a singly charged negative ion, or equivalently, it can be defined as the energy released upon addition of one electron in the gas phase. In older literature, it was not common to consider electron affinity as a quantitative measure of acidity due to lack of data in this regard, in this field. Anyway, electron affinity has serious flaws as a quantitative measure of acidity. Among the main flaws is the fact that electron affinity is the tendency to accept an electron, while Lewis acidity is the tendency to accept an electron pair. There are many cases like radical OH, which has one low energy partially filled orbital, so they have high electron affinities, but they don't have any low energy completely empty orbital. They don't have any low energy vacant orbital, so they are not good as in being a Lewis acid. So the correlation between electron affinity and Lewis acidity is weak in some cases. Additionally, electron affinity is about complete transfer of an electron, but Lewis acidity is about sharing of an electron pair between a Lewis acid and a Lewis base. And so they are fundamentally different. So we see that electron affinity can be considered as a good candidate for a measure of Lewis acidities. In this regard, another related quantity is the ionization energy. Ionization energy is the minimum energy required to detach an electron from a neutral or positive molecule or cation. It is common to consider electron affinity in the case of negative species and ionization energy in the case of positive species. It can be argued that ionization energy has similar flaws like those of electron affinity. However, ionization energy is useful in prediction of general relative order of Lewis acidities, especially for metal cations. Metal cations with higher ionization energies usually have higher Lewis acidities, and general trends of ionization energies of metal cations usually can be considered as a general approximation of their Lewis acidities. In this regard, it is good to consider that acid-base behavior of Lewis acids and bases depend on their electronic structure and properties like electronegativity. And as first approximation, electronegativity can be considered as half of sum of ionization energy and electron affinity, where values of ionization energy are usually higher than those of electron affinity. Anyway, it is not common to consider electron affinity or ionization energy as good candidates for measure of Lewis acidities or basicities due to their flaws in this regard. Among the first attempts to quantitatively measure Lewis basicities, whose usage is widespread in literature, is Gutmann's antimony pentachloride affinity, or Gutmann's donor number. Gutmann's donor number, or antimony pentachloride affinity, is the negative of the enthalpy change in kilocalories per mole at 298 Kelvin for the reaction of the one-to-one Lewis adduct formation between a Lewis base and the reference Lewis acid antimony pentachloride SbCl5 in dilute solutions in the 1,2-dichloroethane as the solvent. The general form of the reaction is as follows. Lb, the Lewis base, and SbCl5, antimony pentachloride, the reference Lewis acid, in dilute solutions of the 1,2-dichloroethane as the solvent, yield the Lewis adduct Lb SbCl5. SbCl5 affinity, or Gutmann donor number, often abbreviated as Dn, is the negative of the enthalpy change in kilocalories per mole due to historical reasons for this reaction at 298 Kelvin. It is good to mention that IUPAC defines donor number as a quantitative measure of Lewis basicity. Also, IUPAC considers the term acceptor number, often abbreviated as AN, and IUPAC in its gold book defines acceptor number as a quantitative measure of Lewis acidity. So for Lewis basicity, donor number; for Lewis acidity, acceptor number. Why it is common to consider Gutmann's donor number as a scale for Lewis basicity, especially in solution chemistry in different fields, it can be argued that Gutmann's donor number has serious flaws and disadvantages. Among the main flaws is the choice of antimony pentachloride as the reference Lewis acid. Antimony pentachloride catalyzes the reaction between amines with chlorinated solvents, like with chloroalkanes, like 1,2-dichloroethane. So we will have problems for the important group of bases, amines, in this regard. Also, antimony pentachloride has more than 100 electrons, so it is not an ideal species for quantum chemistry calculations. It also has relativistic effects which make quantum chemistry calculations harder. Other disadvantages which can be argued are sample of bases considered in the literature, quality of previous measurements, and validity of domain of this scale. A similar enthalpimetric Lewis basicity is boron trifluoride affinity. Maria and Gall proposed boron trifluoride affinity in in 1985. Gutmann's donor number was proposed in 1966. Boron trifluoride affinity is the negative of the enthalpy change at 298 Kelvin for the reaction of the one-to-one Lewis adduct formation between a Lewis base and the reference Lewis acid boron trifluoride BF3 in dilute solutions in dichloromethane as the solvent. So the general form of the reaction can be written like this. The Lewis base and BF3 boron trifluoride as the reference Lewis acid react each other in dilute solutions of dichloromethane as the solvent to yield the Lewis adduct LbBF3. Here we should not mistake this B for the base with this B for the boron. Boron trifluoride affinity is the negative of the enthalpy change for this reaction. These two scales are very similar, especially with consideration of the fact that boron trifluoride and antimony pentachloride have similar Lewis acid characteristics. They both are hard, have high Lewis acid strength, and also can be considered to have some similar steric properties. But it can be argued that this scale, boron trifluoride, doesn't have many flaws or disadvantages of this scale. For example, boron trifluoride has much fewer electrons than antimony pentachloride, so it is much ideal for quantum chemistry calculations. It is good to note that while antimony pentachloride affinity, while it is common to use Gutmann donor number as a scale for comparison of Lewis basicities of solvents in literature, and also boron trifluoride affinity was proposed as an affinity scale for solvents. It is good to consider and note that both of these scales are solute scales, solute basicities, and not solvent scales or solvent basicities. Where in a solute basicity scale, the Lewis base under analysis acts as a solute, while in a solvent basicity scale, the Lewis base under analysis acts as a solvent. So, while it is common to use these scales for comparison of basicities of solvents, we should consider the fact that these are solute basicity scales, not solvent basicity scales. Anyway, scales like these ones are reaction specific. They give order of Lewis basicities for reactions with specific Lewis acids For example, antimony pentachloride in Gutmann's donor number, and boron trifluoride in Maria and Gall boron trifluoride affinity scale. We know from our previous discussions that we can't have a unique order of Lewis acidities or basicities. When the reference Lewis acid changes, the order of Lewis basicities might change. So, the orders of Lewis basicities obtained from these scales might not be correct for some Lewis acids. Among common enthalpimetric Lewis basicities are cation Lewis basicities, usually measured in the gas phase. Cation enthalpimetric basicities are negative of the enthalpy change for the reactions of one-to-one Lewis adduct formations between a Lewis base and a reference cation. The general form of the reaction can be written like this: Lewis base plus M plus the cation yields the Lewis adduct MLB plus. The cation M plus affinity is the negative of the enthalpy change for this reaction. It is common to consider singly charged cations for this reaction, since for double charged cations or cations with higher electric charge, due to higher ionization energies, instead of this reaction, we might have electron transfer from the Lewis base to the cation. A wide variety of cations have been considered in this regard. For example, monopositive cations of alkali metals, transition metals, protonated bases like NH4+, ammonium cation, coordination entities like FeBr+, cations of group 14 like CH3+, halogen cations like Br+, and so on. Among common cations in this regard are monopositive cations of alkali metals like Li+, Na+, K+. It is also good to know that there have been attempts to correlate these scales by statistical methods, by statistics. For example, relationships of this kind: y is equal to mx plus b. The formula of a straight line. X is one of our scales, for example, scale 1, and y is another scale, for example, scale 2. For example, X might be the Gutmann donor number, and y might be the boron trifluoride affinity. Using data of tables, we can use statistical methods to obtain M and B. the slope and the intercept of this linear relationship. Such linear relationships can be used to take value of y based on the value of x or vice versa. And such relationships are valuable in this regard, in prediction of basicities, acidities, or correlation of them. However, while in some cases such relationships give relatively exact responses, answers, there are other cases in which such relationships don't work. So there are a matter of statistics to see whether for two scales such relationships work or not. Another enthalpimetric Lewis acidity or basicity scale is Drago's EC, ECT, and ECW models, and I will discuss them in the next video. This is the end of this online tutorial. I hope you find it useful.